Okay, hello, my name is Jero A. Madrona and I will be presenting this topic, okay, the time delay, effects, and compensatory techniques. And this will be my topic outline. First, let's define what is a time delay, then the effects of time delay, and of course, the techniques to compensate for the effects of time delay. Okay, first is the time delay. Time delay is simply the lag between a control action and the system's response. So, for example, we have here a simple diagram. I have an input, R, as a function of time, and I have an output, Y, as a function of time. Okay? So, the delay is the lag, okay, between this action. Okay, so in your input side, then the output, okay, the response of your system. So this process is your system. Okay. So suppose I have this signal. The yellow line is my input. Okay. So ideally, what we want in our system is that if my input, let's say from 0 goes up to 1, my output will immediately, okay, follow that signal. So which means at this time my ideal output should follow the input signal. From 0 it goes up to 1. Okay, that is the ideal system, but we know in actual process that's not possible. Okay, so there's some delay in our system. So as you can see, my blue line is my output, so my system's response. So from 0 it takes a while, okay, to reach this magnitude of 1. Okay, so that's the delay in my system. So if we're going to measure that delay, that is of course in terms of time. So from here, so it takes, okay, so approximately that is 11 seconds. Okay, so it takes 11 seconds for my process to settle down. Okay, so this time here is your delay. Okay. So what are the effects of time delays? So one of the effects of time delay is the overshoot. So delays in the system can increase overshoot by slowing down the corrective action of the controller. So this time I overlap my input and output signal. Okay, so the yellow line is my target signal. So it has a magnitude of 1 unit, right? So my target is that my output will also have 1 unit magnitude. But in this case, so it overshoots to 1 unit. Approximately this is 1.3. Okay, so this is called the overshoot. So it is higher than the set level. Okay, so that is the overshoot. Next effect of time delay is the settling time. So longer settling time. In this case, my output from 0, so it starts to rise up, it overshoots, then go back, right? Then it settles down at this part of time here. So this is approximately 11 seconds. Okay, so for the settling time, suppose we have a system with a steady state value of 100. So let's assume this one is 100. So we can scale this up times 100, right? So this is my target. Okay, so let's say that is 100 units. So this system has a 2% tolerance band. So which means that the system is considered settled. So when the output stays between 98 and 102 units. So due to 2% tolerance. If the output enters this range at, let's say, 11 seconds and remains within it thereafter, so it means it's settled down, then the settling time is 11 seconds. The common effects of time delay is overshoot and longer settling time. Right? So we have some methods or techniques to compensate for this delay. The first is PID tuning. Okay, so a PID controller calculates the control signal. Okay, this is the control signal. This is my process, or other word for process, the plant. So calculates the control signal based on the error between, so this one, we have error here, between your set point. Okay, this will be your reference signal. Okay, R as a function of T, and the output. So we have a feedback from your output. So some of the signal is feedback to, okay, to your input. So we sum up this one. Okay, the difference will be your error. Okay, so let's assume for this particular controller, okay, so the proportional gain, K sub P is 1, your integral gain, so this one, okay, K sub I is 10, and your gain for the derivative, K sub D is 5. So if I'm going to input some signal here, so my output based on my simulation looks like this one. So it has a overshoot, or it has an overshoot, and it has an 11 seconds settling time. Okay, so we can compensate for this overshoot and your time delay by tuning your PID. So what we mean by tuning is we change the gain. So this let's say gain 1 for the proportional, 10 for the integral, and 5 for the derivative. So okay, we can manually tune that up. Let's say we change the value. So our proportional gain now is 22. So from 1 we change to 22 manually. So we have for the integral, from 10 we change the gain to 12. And for the derivative, from 5 we change to 6. So this is manual tuning, and this is the result. So as you can see, the overshoot is eliminated, and my settling time now is 2 seconds only. Okay, so and there's also automatic tuning for the PID controller. Okay, so this is one method to compensate for the overshoot and settling time. Okay, so you tune your PID again by changing the gain for the respective proportional, integral, and derivative controller. Okay, so the second method is we can use predictive control. One good example is the Smith predictor, which compensates for the long dead time. So the drawback of PID controllers if your system has a long dead time. Okay, so Smith predictor is ideal for this application, okay, for the system with a long dead time. So by predicting the system behavior. So I have here example block diagram of a Smith predictor. So this one will be your control point, right? Your set point. That is your control signal. This one is the model of your process. And this one is your actual process, right? So as you can see, from this compensator, so we branch out the signal from our or through our model and through our process. Okay, this one, y sub 1 is your predicted output, and of course your y is your actual output. So if you notice, it is just calculating the error, okay, between your actual and predicted output. So with that, it is feedback. First, it passed through the filter F, then feedback, okay, to the input. So we have still an error. So continuously the model will adjust, okay, for the error, okay, between the control or the set point is the control signal and the output, the actual. Okay, so this is the simple output signal for this Smith predictor. So the broken line is your PI controller. So based on this, Smith predictor provides a faster response and no overshoot. Okay, so this one has an overshoot. Okay, the broken line with the pink color, that is your PI controller. The solid blue line is your Smith predictor. Okay, so based on the graph, Smith predictor has most stable output signal. Okay, So another one to compensate for the effects of time delays is using MPC, or the Model Predictive Control. So this one predicts the future behavior of using a dynamic model, and it optimizes control actions for the desired performance. So for this block diagram, so this one of course may control signal, okay, or may reference. And I have here a manipulated variable. So this one controls your output. And if you notice, from the output, we also have a feedback. Alright? So this is measured output. Feedback to the MPC. Okay, so it will, again, test against your reference. So this is the sample signal on how this MPC works. Suppose we have this manipulated variable. Yes. Okay, so inputted at this terminal. Okay, so it will this is discrete signal, right? So we are expecting this kind of waveform at the output. Okay, so using MPC, this pink line is your reference signal and this blue line is your output. Okay, so it is a little bit of overshoot. Okay, so these are three of the popular methods to compensate for the time delays. Okay, so in conclusion, so by using PID tuning, predictive control like the Smith predictor, and advanced strategies like MPC, we can effectively manage time delays and ensure system stability. Okay, so that's it for my presentation, and thank you.